All right, so let me just get my camera all set up. Make it go wide camera. Get my nice face there. All right, so looks like I can run this guy here. And I'm wondering if I can set up, give me just a second. I'm gonna go home, recent activity. He's live, so I'm gonna click on this. So I'm a little lag. So I'm gonna upvote, added a like to the video, and I've got one response. All right. So I need to turn the volume down so you can't hear me. So you don't have that echo. I thought we could have a feed that I could keep track of what you're doing or what you're saying. All right, split screen so I can see what's going on YouTube. I'm wondering if I could log in as myself. I'm gonna go back here this way. Maybe I'll have a little bit more abilities. My channel. Switch accounts. Stephen Rains. Activity. See along with a little bit of a lag there. Alright, so I'm now here. I wonder if there's like a, it doesn't show me the people viewing it. It just says likes. Alright. So be it. Hopefully somebody will come in. You can always send me a request on Remind so that if you have any questions and they pull up, you can. What I'm going to do is I'm going to go ahead and start with the review, and I'll start with one and move our way through. There's some questions to remove off of your review. I will let you know that, so kind of give you more of a focus so you know where to go. And then I will kind of give you a little help as to what we need to do from there. So let me get started. I'm going to be looking at number one. I've got to pull up the information here on my document I have. So number one says something along the lines of, how do you determine if a car's displacement that travels 10 kilometers north and 20 kilometers south? What we do when we talk about the adding of vectors, if they're in opposite directions, we give one of those guys a negative, so you end up subtracting, and then you give the direction to whichever number had the greater value. So in this case, if we were to go write that down, we have 10 kilometers north minus 20 kilometers south. that gives us 10 kilometers, and because 20 is greater than 10, the answer would be south. So I subtracted there to help you get that. So it looks like, just looking at my writing, I may have to write a little bit bigger so that we can see. So that is number one. Number two, we are looking at the equation that has final velocity, initial velocity, acceleration, and time in it. So we have to have V, let me write that a little bigger. We need V, we need V naught, we need A, and we need time. We have an equation in your toolbox that is this: V is equal to V naught plus A times T. If I want to solve for A, first thing I'll do is subtract V naught over and then divide by T. So I have V minus V naught divided by T, which is your average acceleration equation. So you can think of it either way. You start here or you use this equation. So on the next one, on number 3, it's going to ask you for the average acceleration, and it gives you a V naught and a V, and as well as a time interval. So you're just going to plug those information in and go from there. V, according to number 3, is it goes to 22 meters per second. And V naught, it started at 13 meters per second, and the time it took to do that was 60 seconds. So if you look at those those variables, if you plug those into the equation, you should get something along the lines of this. So if I come up over here and I say the average acceleration is going to be equal to 22 minus 13 divided by 60, or 9 over 60, or 0.15 meters per second squared. So that would be your answer to number 1, or sorry, number 3. Next thing, that will kind of get you going there. It looks like you might want to try to zoom in a little bit if you can on my video, or zoom out and get it on a big screen. I had it kind of small, so it was a little bit harder to see. I would like to talk to you now about number 4. We're going to do a kinematic equation that does not have time in it. There is only one of those, so that means when we go to do it, we would get rid of time and we would add in a d, or you could say, instead of d, delta x on your toolbox that I normally give you that looks like this with the equations. That guy has delta x on it instead of d, to kind of let you know that. We plug an equation, it should be v squared is equal to v naught squared plus 2a delta x, or d, whichever you prefer. Now what we're going to do with that is we're going to rearrange this guy to where acceleration is by itself. So if I will subtract this guy over here and then divide by 2 delta x, I should get something along the lines of v squared minus v naught squared divided by 2 delta x. Okay, so now that will give us a, plug our numbers in for number 5. And if you look there, 5, the initial velocity was 10 meters per second. The final velocity was 15 meters per second. So V is 15 meters per second. And V naught would be 10 meters per second. And your distance, or in this case delta x, was 30 meters, not 10 meters, 30 meters. So if I come over here and I go to enter that in these values into this equation here, I get 15 squared minus 10 squared divided by 2 times 30. Now what I would recommend you doing, if you do this guy minus this guy divided by 2 and then times 30, you're going to end up multiplying this whole thing by 30. That's been the most common mistake that I have seen. So what I would recommend you doing is do this and then divide by 60. 2 times 30 is 60. Just flop, go ahead and make that 60. You should get something like 125 divided by 60, or 2.15 meters per second squared. Hopefully that helps you through the process. And then we'll look at number 6, 7, and 8 next. Take a moment to jot those down. I'm just going to check in with everybody and see where we stand, to see if I can help anybody or if anybody's trying to communicate with me, if there's some direction I need to go over the last few problems. Give me about a few moments. All right, so you can chat. There is a chat option on the video. Please make sure that you're submitting information to me. If you have a request, if you are watching the video during the live response, and I'll try to answer what I can. I'll keep note of this as I'm watching. I'll look at the information there in the live chat just to make sure I'm covering things that need to be covered. Okay. Please submit questions via live chat. Please submit questions via live chat. All right. So far, I don't have anybody that is asking any questions. I have one watching now. So we'll see if those that are watching, if you could go ahead and give me a response if you need to. We'll keep that going. I'll keep the chat up, and then I will move on into the next problem. So looking at number 6, 7, and 8. So 6, 7, and 8, we've got what is the equation for speed? Hopefully you remember back to your middle school days when you're talking about what is the equation for speed, because that's when you covered this stuff, as well as the beginning of the year we reiterated that. So hopefully you have it down by now. But the equation for speed is equal to distance divided by time. Okay? If we're looking at a graph, then that's number 6. If we're looking at a graph, number 7, of distance per time, and you have something like this. This is an example of constant speed. When you look at this guy, what we're saying is we're not changing our speed. We're covering the same amount of distance each time interval. So if we did a little thing like this, and we can have a little stair step, and it would be the same all the way up. You would notice that this relationship on each one of those hypotenuses would be the same value. Okay? What we're saying is each time interval that we cover the same height, or we cover the same amount of distance in this case. So this would be an example of constant speed. That gets us through number 7. Let's look at number 8. All we have to do is look for a line segment that has a positive change in acceleration. Anytime your speed is increased, you would have an acceleration. So in this case, that's NO. Hopefully that makes sense to you. Pretty straightforward. Number 9 is the one that I really want to talk to you about. So let me erase this guy. Okay. Number 9 has a graph that looks like this. Distance, time, and we're doing something like that. Okay? What I want to make sure we get on number 9 is this. Let me make sure I'm on the right problem. All right. So, number 9. We are increasing the rate that we cover distance each second. So we're increasing our speed. When we look at this graph, the distance covered each time interval is increasing at an exponential rate. Okay? So when we look at this guy, he's increasing by a quadratic. What that means is that in the first second we would cover 10 meters, or maybe 1 meter. The second 2 meters. The third second, 4 meters. The fourth second, 16 meters. And then so on and so on and so on. And you see it get dramatically increasing. Okay? Well, that's what is happening to the distance. Here we are changing our speed. Okay? As we change our speed, we are changing it at the same rate. So that rate that we're changing would be a constant acceleration. So distance is exponentially increasing. increasing at a steady rate. And acceleration is constant. Okay? So far I don't have any questions. If you do run across anything, please let me know. The live chat option in YouTube, it seems like I have 2 people watching now. So that increased in the number of people that are watching. If you want to give me any questions that you may have or concerns, use the live chat option down at the bottom, and it should pop up or notify me if you have a question, and then I can try to address that. Hopefully, I'm sure if you have a question, there are more than just one, so if you would go ahead and share them, please let us know, and we can keep going. Number 10 we're going to answer, but number 11 and 12 you're going to mark off your review. Okay, they were ones that I wanted to remove off, but go ahead and take those off now. I just forgot to remove them off before I printed. So looking at number 10, we're talking about an object falling, or a person falling, and we're going to consider their velocity positive. If the velocity is positive, if this is where they're going and we say that's positive, when they release their parachute, that guy is going to slow them down. So their velocity would be slowing down. So we have a decrease in velocity. If we decrease our velocity and we're going in the positive direction, then we always consider that a negative acceleration. So we do a negative acceleration. Okay? Hopefully that makes sense to you. We're going to move on to 13. So let me go ahead and get that going. Okay, so on 13, we have 2 problems back to back that are kind of about the same thing. 2 cases. One, we have a book, or a brick, I think is what it calls it. I used a book in class. We have a brick, a student is pushing, they apply a force this way of 5 newtons, and the friction force is going back of 5 newtons. For all intents and purposes, we don't really know whether the book is moving, or brick is moving or not, from what the problem says, but we know this. If these guys are the same force and equal in opposite directions, then the net force on this guy would be 0 newtons. Okay? Net force is equal to 0 because they're equal and opposite. We would subtract those vectors. Earlier, we had 2 vectors in opposite directions and we subtracted. We took 10 and we subtracted 20. And so that gave us 20, and we gave it the direction in the one that was greater. Well, in this case, they're equal and opposite, so we get a 0. This book could be moving at a constant rate, or it could be stationary. Either way, we know that this guy is in equilibrium because its net force is 0. If we add or subtract these 2 guys, we get 0. Number 13 is kind of along the same lines. I believe it's 13. Let me double check. 14. Number 14 is the same lines. So it says something along the lines of this. It has moving 2 meters per second. There is a force going this way of 10 newtons, and another force going this way that we don't know. Okay? This guy is moving 2 meters per second. It's not accelerating. It's showing it's a movement of 2 meters per second. So that means it's not changing its motion. It's in equilibrium. If it's in equilibrium, the only way you can be in equilibrium is have a net force of 0. Well, if 10 newtons is going this way, then this force has to be 10 to give it a net force of 0. So we get force 1 is equal to 10 newtons. Does anybody have any questions over that? if you can use the chat feature in the live video down at the bottom, it says live chat, to be able to send me questions if you have them. And we'll keep going, and I'll move on to 15. This is pretty straightforward. Whenever vectors are in the same direction, we add them. When they're in opposite directions, we do as we've done here and subtract them. But as in 15, if the vectors are in at parallel to one another, or not parallel, perpendicular to one another, then we have to use something else. So number 15, we have two vectors. One of them is south, and the other one is west. So we sit here, we've got a vector going this way, that's 4 newtons, and we got a vector going this way, that's twice as long at 8 newtons. If we were to transpose this and kind of draw it over here, then we would see that we have a hypotenuse of a triangle. So we want to know what the resultant vector is. The way I have shown you is I have said do resultant 1 squared plus resultant 2 squared, or vector 2 squared, and then that will equal the resultant squared. You can rewrite this, and I recommend to go ahead and do this for yourself, to rewrite it like this instead, because that's what you're most commonly used to. So we're using Pythagorean theorem here. 4 squared plus 8 squared equals c squared. We've got to take the square root to solve for c. So we get 4 squared plus 8 squared equals c squared, and take the square root of both sides. This is 16, this is 64, so it's the square root of 80 is equal to c, or the resultant vector. Square root of 81 is 9, so we're looking at something that's just under 9. More than likely you'll get something that's 8.9, and this is in newtons, so you can get that. Do we have any questions thus far? Pretty straightforward. All right. I'm looking at number 16. On number 16, I am, we've got, it says, what is the equation for the change in momentum or impulse? So looking at momentum or impulse, there are two ways to look at that, a change in momentum or impulse. They are the same thing, but with different variables, come out to the same answer. What I mean is this: impulse letter on your physics equation sheet that I gave you, here is the letter J. That stands for impulse. It can be force times time, or it can be a change in momentum, which, if we were to write that out, would be mass times a change in velocity. That's a small v, not a big V. Big V stands for volume. Small v stands for velocity. So mass times a change in velocity would be your answer on 16. Now, 17, one of the things we see is this. It gives you several variables there, but the ones that matter is the mass and the velocity. If we want to find the impulse, we can come right down here and find mass times the change in velocity. So the first thing I'm going to do is write down my mass is 0.01 kilograms. And my delta V, well, let's figure that out. The first thing I need is a final velocity and V naught, or initial velocity, or the starting velocity. So we stopped it. It was moving 6 meters per second. So that means that the initial velocity was this. It came to a stop. So we came to a stop. That means that the final velocity was 0. When I go to solve for this guy up over here, I'm going to do mass times V minus V naught, or 0.01 times 0 minus 6. Okay, you should get a negative answer here because we applied a force in the opposite direction that it was coming. So I would have had a negative acceleration there. So that force will be negative. The answer for the impulse will be negative as well. And because it's asking for impulse, the units is Newton seconds. So when you multiply those two together, you should get a negative 0.06 Newton seconds is your answer for 17. Do I have any questions? We good? So far, I've got several people watching right now. If you have some questions, let me know, and I'll keep going from there. Number 18, equation for momentum is this guy here, but we don't have a change in momentum. There's no change in delta V. There's just V. So momentum is really mass times velocity. In this case, you have 1,200 kilogram car, and you are moving 30 meters per second. Gives you 36,000 kilogram meters per second. Okay? Hopefully that's pretty straightforward for you, and we can kind of go from there. I would like to start looking at number 20 and 21. So take a moment. I'm going to back out of the way. If you want to pause the video, you can, and you can jot down anything that you might need. I'll kind of get you a break to kind of catch up, and then I will start writing 20 up over there on the far side over here, and we'll do 21 right after that. It's time for a new marker. Any questions? We good? All right, I'm going to go ahead and move on to 20. So this is an elastic collision. I have knots in here because this is before the collision, so we're going to call these the initial velocities of both these objects before they collide. Then after they collide, look, the knots went out of the way, so that means these are the final velocities after the collision of each of those objects. If the masses are the same, then basically what we'll see will happen is this V naught will be here, and this V naught 2 would be here, if the masses were the same. I'm going to go ahead and have you write it this way, though, because we don't know that the masses are ever the same. So we would do this way. Now, the good thing about it is it wants to know what the final momentum is. So really, we could just say, what is this? I want to know what the final momentum of this object is. Okay, we don't have to figure out all that. We just have to figure out this side of the equation. These two objects are running at each other. So first thing we need to know is that these velocities have a vector quantity to them. One guy is going to end up being a negative so that we can figure out what's going on here. The mass of the first one is 2 kilograms, and it is traveling at 10 meters per second. We're going to add that momentum to the other car, and it is 5 kilograms, traveling at 4, is that right? Meters per second in the opposite direction. So I'm going to give it a negative because it's traveling opposite. Okay? So when I look at this guy, that means that 2 times 10 is 20. And then if I add it to the other one, you would get negative 20. And the overall total momentum would be 0 kilogram meters per second. Now, what that means, we would expect that this side of the equation, when we figured them out, would end up equaling this. So their momentums actually transfer. Whatever this momentum was here becomes the momentum of this car. And whatever this momentum is here becomes the momentum of this car. so that when we add them up again, we get 0 kilogram meters per second. That's the conservation of momentum. Now the good thing is that number 22, we're not going to do. So you can mark out 22. 23 and 24 are basically saying the same things. So what we need to make sure we understand for 23 and 24 is the work equation. Force times distance times cosine of theta. Okay? Now for 25, what I would like you to do, and I've told all students this, including you guys now, for number 25, I need you to mark out the words and write down the problem that I give you. I selected that problem, and then when I started going to make the test, I was like, I really don't like the problem at all, but we still need to have some work, and I still want you to do a practice over that. So what I ended up doing is I want to know the work, and what I've been telling everybody today is that 300 newtons is your force. The distance is going to be 3 meters, and the angle at which you're going to apply the force is going to be 30 degrees. Now what we're saying is we got a horizontal surface, we have an object here, and I'm going to push an object with 300 newtons of force over 3 meters at an angle of 30 degrees. Okay? That's what we're saying. I want to know the work done. It's going to be less than if I was pushing it horizontal. So I'll plug this information in, and I should get work is equal to 300 times 3 times the cosine of 30. Make sure you're in degrees, and if you do that all correctly, you should get something like 779.4 joules. And that will get you number 25. So of the 3 of you guys watching, do y'all have any questions? If you would like, you can go ahead and submit a chat response. I'm just going to see if you guys can do that or not. It is good for me to know if I can see that chat. You can just say all good or no thanks or something like that. If you could do that for me, that would be great. That way I know that chat function is working for us. All right. Number 26. How do we solve for final velocity with initial velocity, acceleration, and time? This is the easiest equation I have for you today that I know of, aside from the momentum equation. So number 26, you're going to use V, or final velocity, is equal to V naught plus AT. Okay, pretty straightforward. That can be found on this guy here. Okay, and that is the one of the equations in your kinematic section, or Newtonian mechanics, I think is what they call it on the sheet. In this case, it says a car starting from rest. So if he's starting from rest, he goes away, and you could say you can go up this way, it's 0, right? That leaves acceleration times time. It says that the acceleration was 5.0 meters per second squared, and we did that for 8 seconds. If we multiply those two together, you should get 40 meters per second. How do I get the unit meters per second? Well, this guy has 2 seconds in it, and you're multiplying by a second, so one of the seconds go away, and that leaves you with meters per second. All right, let's move on to the more complicated stuff. Thermodynamics. So, what I'm going to do is I'm basically going to give you a crash course in what we talked about for the last couple of weeks in this last bit of section. So what that means is you're going to have to bear with me. It might be some content, but we should be able to give a good hold on that information so that we would be good to go. Now, one of the things you need to make sure you're able to do that is not on this review, but I felt like this was the most common thing that everybody was okay with, that was energy. So kinetic energy is equal to 1/2 mass velocity squared. Make sure you know how to use that equation. as well as GPE, mass times gravity times height. Those are two very common equations that everybody's really good at and easy for people to use. And so I didn't put them on your review, but it is possible that you see those on the test. But now, thermodynamics. So, first law of thermodynamics. To change the internal energy of a gas system, so a system of particles, if you will. Internal energy, if you want to make a note, it is U, capital U. Okay, that's internal energy. We have two options: add or remove heat. So if I were to give symbols to that, what I would do is add a plus here, or I put a minus here, and then over here I would put Q. Add or take away, remove heat. Another way to look at this is work is done on the system, so the set of gas particles, or by the system. Okay? If it's done on the system means we're compressing this guy. We're taking the gas and we're compressing it. So say I had a cylinder here and a piston, and I was pushing down on the piston. If we didn't add any heat to that or take any heat away, because we're decreasing the volume, that pressure and temperature would increase. Okay? So we're closing the volume in, we're making it get closer, so the temperature, the internal energy, guys, would increase. So this guy would actually be what's called, referred to as a negative work done. So negative work done, and U increases. Internal energy increases. Okay? So this is a, if you will, negative work done. Okay? Having trouble drawing stuff, writing stuff here. Negative work done. All right? Now, over here, by, what that means is that the gas is expanding. We're allowing the gas, so it's the reverse of this guy. The gas is pushing up, and as it presses out, you're going to find that it gets lower. The internal energy decreases. So this would be a positive work. And internal energy decreases. Internal energy decreases or goes down. Okay, we'll take a moment. It looks like I might have the chat function. So Kimberly, do you have a question? Seems like you got the chat function working. Oh wait. Yeah, I know it's lagging pretty. It has a little bit of a lag, but it's not too bad. So if you come across any questions, I will be checking it out to see what's going on, and kind of go from there. So I haven't really gotten to 28 yet, but this is just kind of an overview of what we've talked about for the first law, and it's going to help us get an equation. So basically, we say this: if I want to change my internal energy, I'm either going to have some sort of heat, or I'm going to have some sort of work. The minus work is here because of this. When work is done, to make U increase, we have to make it negative. If I make this a negative work, that makes that a positive, and U will increase. If I take this guy and put in a positive work, well, that means that the U will decrease, because it's a subtracting work there out of it. So I want to make sure we understand that principle, and this is the first law of thermodynamics. So if you look at the first law of thermodynamics, it says deals with the energy transfer and is a restatement of. What we are talking about here is we put energy into a system, and that energy should be not lost or, not destroyed or created. It's conserved. So we refer to, if we look at number 30, look at it real quick, I'm jumping around just a second. Number 30 refers to the law of thermodynamics and a restatement of the law of conservation of energy. So if you'll jot that down real quick, that kind of helps us get through that law. Now, if you look at number 31, you'll see this equation here. Okay? And then I'll jump back and I'll talk about this 28 and 29. But number 31 is basically the first law of thermodynamics, and it says, what is the heat release if the change in internal energy is a positive 10 and the work done by the gas is positive? So work done by, so notice this is on, and that makes it would be a negative work, but it says work done by the gas, that means it's a positive work. So if it's a positive work, if we want to solve for Q, I'll add W to both sides, and I should get what you have on your review of delta U plus W equals Q. Now, I have 10 and I have 25. Both of those are positive numbers. I plug them in. You should get 35 on number 31. So let me go ahead and write that down. Delta U, it said, was 15 joules. The work done was 25 joules. And we'll add them. Is that correct? Not 15. It was 10. Oh, the internal energy was 10. Yep, that was right. And work done was 25. So we'll do 10 plus 25 would give us 35. 10 joules plus 25 joules gives us 35 joules. And that is number 31. Okay? Now, that should get us to where we need to be to go back and answer the total entropy of the universe. So what the second law states, and that's going to get back down to 34, the second law states that a heat-efficient engine, there is not one that's 100% efficient. And what that means is that as we do these processes, all natural processes lose energy to the environment. So that's the second law. So hopefully, if you need to, pause my video. You can get caught back up in just a second. And jot that information down as we have it. And then I'm going to write down the second law so that we can move on into the third. So the second law states this. All natural processes processes lose energy to environment. Remember, the environment is just anything that is outside of the gas. Environment. Or it gives us this equation. QH minus QC is equal to work done. And that means that if I put in heat, so in heat, and some heat leaves to the surroundings, then whatever the difference is work done. And if we want to know how efficient that engine is, then we take that QH minus QC and we divide by QH so that all the units go away, we don't have a unit, and then we'll have something that should be less than 1. The second law of thermodynamics is telling us that it'll never have a 100% efficient engine. What that means is that there's always going to be some energy. This guy right here where it says loses energy, this is always here. Okay? And so because of that, we'll have something that's less than 1. So on your test, a lot of you missed this on your test. I gave you two options that were way greater than one, and one that was a decimal place. You didn't even have to do any math, because if I give you a multiple choice test and only one is a decimal place for efficiency, then that's the only one could be the answer, because it can never be greater than one. So we'll look at that in just a second. That should be number 34. Okay, but I want to go back. I want to make sure we answer 28 before we go any further. So the third law states this. Okay, because of this guy.